Hello everyone, in this video we're going to talk about stochastic analysis. Just as a very brief intro, stochastic analysis is about dealing with uncertainty. So instead of assuming that all inputs are fixed and perfect, we recognize that real-world conditions vary, and we use probability to model those variations and understand their impact on performance. So in any real-world system, uncertainty we know is unavoidable. It comes from both controlled and uncontrolled variations in the design and environment, and these uncertainties affect the system performance and can lead to unexpected results if not accounted for. So we categorize sources of variation into several types, like physical uncertainty, like variability in loads, boundary conditions, or geometry. Also in loads, like vary direction, magnitude, or include random noise, and many more. Now here on the right, this diagram shows how both controlled design variables and uncontrolled noise parameters flow into the system, affecting the output or our design performance response. And by performing a stochastic analysis, we can model these uncertainties and understand how they impact the reliability and robustness of the design. Now we're going to go to HyperStudy and perform an example. So here we are going to investigate uncertain parameters of a cantilever I-beam model defined with 4 variables and 4 functions in here. So we're going to add a new approach. This is going to be a stochastic analysis. Now, in this case, we need to modify our input parameters, the distribution. So for the web thick, flange thick, and flange length, we're going to define this as random parameter. And this is just uncertain, not controlled by the design. And the total height we're going to set to design with random, so uncertain but controlled by the design. And for this example, we're going to let the distribution to be normal variance. So this means that parameters could take random values following normal distribution around their nominal values. Now let's go to specifications. In here we are going to select simple random, and we're going to modify this to be 500 runs. Now we're going to hit apply, next, and let it run. Okay, so now we can go directly to the evaluation scatter. And this plot shows the results of our stochastic study by plotting the total height on the x-axis and the web thickness on the y-axis for multiple design evaluations. And we know that each dot represents a single run with randomly sampled inputs based on the distributions we define, right? The red dashes lines show the constraints. In this case, the web thickness must be between dot 18 and dot 22, and the green dashed line on the x-axis indicates the limit for the total height. And from this plot we can see how much variation there is in the design responses due to input uncertainty, and it also helps us identify how many designs fall within the acceptable range and spot any trends or clustering that may be important for robust design. Now we can go to the post-processing and let's see the distribution. Now these histograms illustrate the spread of values for our key input variables, such as the web thickness or the total height. And in the histogram we see the bars representing the frequency of sample values within specific ranges, and the red curve indicates the probability density function, showing where values are most likely to occur, and the green curve represents the cumulative distribution function, which helps us understand the probability of a variable being below a certain value. Okay, so for instance, for this wave thickness, we observe a bell-shaped curve centered around the nominal value, reflecting a normal distribution, and this suggests that most samples are close to the mean, with fewer at the extremes. And in contrast, this total height plot may show a truncated distribution due to design constraints, indicating that while we have variability, it's within specified bounds. Now let's go to the reliability, and I added these three responses, and I added the bound value for the nominal design. So this just means that there is a 49% probability for the moments of inertia and the displacement to have values different than the nominal design. Now we can check also the reliability plot for, like, for instance, the moment of inertia, and this curve shows the probability that the moment of inertia will be greater than or equal to a given value based on the stochastic analysis. So for instance, for this graph, we can interpret two key points. The 95% reliability level occurs at 61.47, meaning that 95% of the designs have a moment of inertia values above this threshold, and the 5% reliability level is at 90.41, meaning that only 5% of designs exceed this higher value. And this plot helps us understand the likelihood of achieving certain performance levels, and it's especially useful for reliability-based design, ensuring that our design performs well even under uncertainty. Thank you.